Welcome back, class. This is GT 501, lecture 3. Today, we're going to review dynamics and vehicle dynamics. For those of you who has ME background, this will be just a quick review of dynamics you learned in undergrad. For those of you who do not have dynamics background, this may be a good opportunity for you to quickly learn dynamic model of vehicles. So, but this will not cover vehicle dynamics, thoroughly. And there is a separate course in ME department on vehicle dynamics and control. Luckily, this course focuses on longitudinal vehicle dynamics, which is relatively simple in terms of dynamics. Okay. Right, the outline looks as follows. It's like this. First module is going to be review of dynamics. And then second part is going to be the vehicle dynamics. I can move pretty fast on the review of dynamics, as we are more interested in the dynamic model of the vehicle, and the actual contents of vehicle dynamics. The second part is more directly related to our interest. So I'll move fast in the first module. And the vehicle dynamics consists of different components. From three-dimensional space, in three-dimensional space, things are coupled in reality, but we are going to try to, decouple different dynamics of vehicle and try to sort of analyze and look at these equations of motions to understand how vehicle dynamics can be modeled in a simplified way. Okay. Review of dynamics. Introduction to dynamics. Kinematic relationships are used to help us determine the trajectory of a golf ball, the orbital speed of a satellite, and the acceleration during acrobatic flying. These are just a few of the big dynamics that are involved, but in reality, all kinds of things are in motions, and describing these motions are basically dynamics. And dynamics has two components. One is kinematics and the other is kinetics. Kinematics is more of a geometry of a motion, relates displacement, velocity, acceleration, and time without reference to the cause of motion. Okay. And then kinetics is a study on the relations between forces acting on a body, the mass of the body, and the motion of the body. So the kinetics is what's explaining, describing the consequences of applied forces on a body. Okay. Whereas kinematics is simple geometrical relationship. You can think of it as constraint. And kinematics is used to predict the motion caused by given forces. or to determine the forces required to produce a given motion. For example, we are going to have to deal with position, velocity, acceleration. And position, sorry about this font, small font. I think you shouldn't have a problem. I think it's a problem on my side. Anyway, so we have, when it comes to dynamics, describing motions, we need to be able to describe position, velocity, and acceleration. And of course, these are all related. And I think all of you are familiar with this because this is covered in freshman undergrad physics. So first of all, the motion of a particle is known if position coordinate the particle is known for every value of time t. So let's say the position is described by this function, okay? And we want to find out velocity and acceleration of this particle motion. One way to compute that is taking derivative of the position, and we get dx dt equals dx dt equals velocity. And if we plot that as a function of time, then this is what we get. And if we want to find out acceleration, then we can take derivative of velocity one more time. Then we get this function, and the function looks like this here, linear function. And we can also relate this in backwards manner. So we can calculate velocity and position for given acceleration. And we can do that by integrating this over time. So if we integrate this over time, then we get this function. And if we integrate this over time, then we get this curved function. And these relationships is just these are kinematic relationships because they're physically simply related by physics and kinematics. If after for a given amount of time with some speed, you will travel this much of distance. This is kinematics, okay? And there is no force involved. Usually force is involved with acceleration. Anyway, so that's kinematic relationships, an example. And this example shows an example problem. So if there is a Prius decelerating with negative acceleration given by this function, and the initial speed is 60 km/h, and finally stops at 0 speed. And the problem is we want to calculate time taken during the deceleration. And this is the solution. So we have acceleration given. So we want to take integral. Want to integrate this over time and velocity. Then we can compute final time, because that's the only unknown value if you solve that equation. Of course, this one requires these initial and final state to determine the time. Okay. So again, this is simple review of dynamics. Hopefully, all of you are familiar with these. Okay. Dynamics of a point mass. So this falls into kinetics, and there's this, famous Newton's law, right? So there are three laws. The first one is the concept of inertia. So a body will remain at rest or moving at a constant velocity unless it is acted by an unbalanced force. So it's introducing this concept of inertia, and it wants to stay there, stay its speed, whatever that is, unless there is a external forces acting on it. And second law is the famous F equal ma, which relates force with acceleration for a given mass. And this relates, this describes the dynamic motion of a body, whether it's a point mass or rigid body. It can describe the motions because we can take integral of this to find velocity and positions. And then third law is about action and reaction. So there's always, if there's an action, there's always a reaction force acting on the counterpart of the body. But it has to be opposite in direction. So, for instance, if you're pushing a ball and you're applying force, then what this is showing is that there is reaction force acting on your finger. Okay. So if you're pushing a ball or whatever on the surface, you'll be applying external force on that body, but there will be external opposite direction reaction force acting on the tip of your finger. Okay, but obviously, you have bigger inertia, you have resistance, such that you can push the object forward. Okay, so your finger doesn't bounce off. Okay, so all of this will be related to vehicle dynamics, because you can think of this ball as vehicle body or tire, and this, you can think of this finger as the ground. So if you apply torque on your vehicle wheel, then you're creating torque is translated to translational force on acting on the body, which pushes the vehicle forward. But that means there's same amount of force acting on the ground. Okay, obviously there's ground has large inertia. Constant force acceleration example. Assume PS generates constant tractive force. In a motor of PS generates constant tractive force during the acceleration. What is the acceleration of the vehicle? Well, I think this is extremely straightforward. You just need to compute this equation, which is summation of all the external forces equals to MA. And this is the solution. I think that's just too easy. And now it moves to rigid body dynamics. So far we talked about point mass dynamics, but here from slide 10, I think 10 to 13, we are going to talk about two-dimensional space examples and theory. Here, the equations are, you can find these equations from sophomore year dynamics textbook. This is just two-dimensional example of the one we just tackled, and we're not really going to really use these equations in this class, so I'm just gonna move forward, fast forward this slide. But you can take a look at this slide and sort of refresh your memory. And for those of you who do not have any dynamics background, you might want to take a look at these equations and get familiar with this. It'll be a good exercise and practice, learning experience if you do not have any dynamics background. By the way, conceptually, to summarize, in 2D rigid body example, it's a little more complex than point mass dynamics. And one of the main difference is that there is this, because it's two-dimensional, there is a tangential acceleration and normal acceleration. And then there is speed and acceleration relationships. These are kinematics of rigid body, coming from geometrical relationship, and it can be more complicated once you get into three-dimensional space. But again, we're not going to dive into that. Here, what is shown is, but we do need to understand rotational speed and rotational position, speed, and acceleration. And just like the point mass example, their relationship is simply can be computed by derivative and integral. Okay, so derivative of position is speed, angular speed, which is omega, and derivative of that is acceleration, angular acceleration. So, and So far, this was kinematics of a rigid body. So we talked about translational kinematics and rotational kinematics of rotations. And here is an example describing kinetics of a rigid body. So when it comes to 2- or 3-dimensional examples, things can be more difficult to visualize and understand and analyze dynamics. So what people often use is draw free body diagram and kinetic diagram. So this is called free body diagram. And this one shows, so this is a step. This is the sorry about that. So free body diagram, you can draw a free body diagram. In this process, you need to isolate each body. If you have multiple bodies, you need to separate those bodies and then draw the body and put axis on the body and draw applied forces such as P, replace supports with force. This one, and put the dimensions on and kinetic diagram. So this is an example. So draw axis and put forces acting on the body. Put the coordinates, supporting node which provides supporting forces acting on the body, and then we can draw a kinetic diagram that shows the translational and rotational motion of the body. Okay, so in many cases we want to find out acceleration and angular speed, but sometimes in some problems, for given these values, you might want to compute P and vice versa. So anyway, so these relationships will be used for modeling purposes later on. Okay. So in this example, we have translational speed at G, and that point G has acceleration of ax and ay, x and y direction, and then we have angular acceleration alpha, and these three variables can describe all the motions of this bar, but the external forces are these P, mg, cx, and cy. Okay, and this slide summarizes variables, commonly used variables for dynamics, and you should definitely get familiar with this. Okay. For translational motion, we have position, velocity, acceleration, mass, force, work, which is in joule, force is in Newton. Power is joule per second, okay? So work divided by time, okay? And energy is joule. So energy and work has same unit. So and energy is power. So integrating power over time, okay? So that's that. And this, some of you may not be familiar with variables for rotational motion. Okay? So angular position, theta, angular speed, omega, alpha, and J is the inertia, which corresponds to mass in translational motion. And torque, you can think of that as force in translational motion. And work, power, energy is identical to the translational motion. They both have joule per second, or watt and joule. Okay, so both translational motion and rotational motion have same units for work, power, and energy. That's important. But torque and force has different units, because torque is usually this. Let's say there is a bar, you have force acting on it, and there's this distance r. Then torque is force times radius. Okay, so that's why you have this meter, which is, this is a meter. Okay, this distance is a meter. So torque is force times this distance. You know, say, assuming this is rotating with respect to this point. Okay. So this figure illustrates these variables on an object. So this was really quick review of dynamics, and we're going to talk about vehicle dynamics. Vehicle dynamics. We need to first define and have coordinate system and notion straightened out. So there are two types of coordinate systems, but we're going to introduce. I'm going to introduce you to SAE, body fixed coordinate system, and rotation. This figure shows XYZ coordinates fixed on the body, the vehicle, and X is the forward direction, the longitudinal direction. Y is the lateral direction, and Z is the vertical direction. There is another coordinate which considers Z into the upper direction, but we are going to keep it this way. Okay. And so XYZ, I think XYZ is straightforward. And there are 6 more variables because we have speed. I'm sorry, we have 9 more variables to introduce, which is translational velocity, which is U, V, W. And then we also have angular position or angular displacement, which is phi, theta, psi. And phi is with respect to x. So this is roll motion. And theta is with respect to y axis. So it's a pitch motion. And there's psi, which is rotating about z axis. So that's going to be yaw, which is psi. And we also need to define angular velocity variables. So we often use phi dot or p, okay, and q for theta dot, and r for psi dot. And so p roll, q pitch, r yaw. And then there are force and moments acting on the body. We have longitudinal force, lateral force, z direction force. We have x direction moment, y directional moment, and z direction moment. So, and then there's also Earth fixed coordinates. Okay, so this is Earth fixed coordinate, and so we have, this is two-dimensional top-down bird's eye view, and this is body fixed, and this one is Earth fixed. And from Earth fixed point of view, we also need to define some more variables to describe vehicle motions, because let's say vehicle is traveling in this direction. This is the vehicle speed vector, okay? And this vector can be composed of two vectors. One is going to be the heading angle vector, and there is this side slip vector. But in this case, we can simply use scalar in this two-dimensional example, and you can actually just add these two values, beta slip angle plus this psi, which is the yaw angle. Okay, so this is the yaw angle, and this is the slip angle, and if you add them together, then you have this horse angle, okay, which is nu. Okay, and this from body fixed coordinates, you will always have be able to observe a beta, because there's only difference between heading angle and vehicle speed vector. Okay. With those coordinates defined, let's derive equations of motion. This looks ugly, but let's go step by step, and it'll end up okay. Okay. Let's first derive two equations of motion. Translation of motion, rotational motion. Okay, that's a typo. So we have sigma f equals to ma sigma m equals, well, h dot, which is more complicated than this MA, because we're here we are driving these equations motion for three-dimensional space. So we have 6 degrees of freedom, 3 and 3, 3 for translation and 3 for rotation. So we're dealing with 6 degrees of freedom system, object, body, and we have quite complex equations of motion when it comes to both translational motion and rotational motion equations. But we can simplify things. So let's take a look, okay? So if you use acceleration vector and take derivative of that, this is going to be what you get. And again, because this is three-dimensional space, you have pretty long equations. Especially here is a cross product, and here is this term corresponds to the longitudinal speed, lateral speed, and vertical speed, and you have this cross product of PQR, which is rotational speed, and translational speed, and that's coming from this three-dimensional space dynamics. If you write this out in 3 equations, this is the final equation you get. And let's move on to rotational motion, which is m equals h dot, where m is external moment acting on the body, and h dot is basically equivalent to ma in a rotational motion sense. And it's a little more, it's even more complicated because we're dealing with three-dimensional body, and there is these inertia terms, rotational inertia terms, which is 3 by 3 matrix. So anyway, again, this, if you list out 3 equations from this vector form, these are 3 equations you get. This is the final equations you get, which is long and which is ugly, but it gets better. Okay. So this was a full general 3D rigid body dynamic model, not necessarily vehicle, but if we assume vehicle model where we can apply some assumptions, then these equations get simplified. Okay, so we have the 6 equations, and if we apply some assumptions, such as vehicle is symmetric in XZ plane. What that means is if we have a vehicle pointing this way, have a body, let's say this body, this body, and then pointing forward, the left and right part is symmetric, then this inertial terms becomes 0. Okay, and if also PQ, V, and W are small, if we assume this, so what that means is the rotational speed of a vehicle is small, then their products are negligible. small angle. I'm not sure if you're familiar with small angle theorem, but sometimes it helps analyze things analytically. So, say small angle, theta times, I don't know, phi equals close to 0, kind of thing. And if you apply that, their products can be negligible. And U equals U naught plus U prime, where U naught is some baseline speed, and U prime is the delta speed change with respect to the base speed. And if we assume U prime is small compared to U naught, then the equation, these 6 equations, get simplified. And this is the final equation you get after applying these assumptions. This one looks not bad, right? So for instance, these go to 0, these go to zeros, these go to zeros. Many of these terms goes to zeros, okay? These go to zeros and so forth. So if you apply those assumptions, then this is the 6 equations are what you get, and we can move further from here, and we can group things together. So for instance, can you guys see couplings between these equations? If you see, these two are coupled, right? RP, right? And this one is also coupled, right? And these two are coupled. And this one is independent, right? So we can group these into 3. 1, and 2, and 3. 3 groups. And the first one corresponds to longitudinal. And the second one, I'm sorry, let's say this is number 2 and this is number 3. The second one is lateral motion, yaw motion, roll motion. And the third one is vertical motion and pitch motion. So we have 6 simplified vehicle model showing right here. This is it, 3-dimensional space, simplified. But luckily, it still looks pretty big model. But luckily, in this course, we don't really need to handle these equations. All we are interested in is this equation, longitudinal motion, which is good, right? So I just wanted to show, general vehicle dynamics equations of motion and how those are derived, but rather than just showing you this equation, okay? So I want you to have this general, vehicle dynamics model concept, and if you're interested in lateral motion or vertical motion, then you will be handling some of these equations. But in this course, we're talking about powertrain, and we're mostly the modeling we are interested in is going to be only longitudinal motion, okay, which is the simplest dynamic model, okay? But the powertrain will be more tricky to model. The vehicle dynamics itself is quite simple, but powertrain is going to be more tricky to develop a model. Okay. So again, equations of motion. So F equal ma. Forward direction, and F, but there's multiple axes, forces, right, acting on the body. So there's aerodynamic drag, and then there's gravity, and then there's rolling resistance acting on the wheels or powertrain, and then there's tractive force. In the case of front wheel drive, the tractive force will be at the front wheel, and if you write down the equations of motion, this is what you would get. F equals ma. So if you know all forces, then you can compute acceleration. Okay, so m is known, and if all of this is known, then you can find acceleration. And if you integrate that over time, then you will compute velocity and position. Like I said, the vehicle dynamics itself is relatively simple, but when it comes to modeling powertrain, drivetrain, it gets more complicated, and you need to understand their operating principles, how they operate, and how they are modeled. Here, I'm just going to show you a quick summary of powertrain model for conventional engine powertrain. Conventional powertrains usually have an engine, torque converter, and transmission, and then final drive connected to the wheel. And if you look at this equation, we know we're going to look at each force terms here, okay? And that's what this slide is showing. So this slide is trying to compute what Fx, tractive force, is, okay? And tractive force is coming from the powertrain. And this equation is describing the tractive force coming from the engine with different loss terms and so forth. We can compute Fx. Okay, I'm going to talk more about this later on. Okay, but please take a look. We can talk more about this in the discussion session if you have any questions. Road load, aerodynamic drag can be modeled by this equation. This is, physics-based model, and it can roughly estimate. It can estimate some aerodynamic drag using some of these simplified coefficients, which is aerodynamic drag coefficient and equivalent frontal area of a vehicle. So once you have those numbers and vehicle speed and air density, you can compute aerodynamic drag. And you can see some examples of aerodynamic coefficients from different cars. So in the old days, it started with high number, and with all the aerodynamic technology coming in recently, now it's getting lower than 0.3. So lower the better, which is less resistance. Road load, rolling resistance is right here. So this is acting on the tire, but rolling resistance is everywhere in the drivetrain. Basically, tires, bearings, and so forth. Anything that creates this friction. So, but one of the biggest cause factor of rolling resistance is a tire, because it's made of rubber. And if you go through, and this value can change as a function of with respect to the road condition. So this figure shows that. And also temperature also has an impact on that. So this is what's determining this rolling resistance. And there are tires with low rolling resistance, and some eco-friendly vehicles, like hybrids and EVs, often equipped with low rolling resistance to maximize its range and efficiency. Okay, so let's now turn to lateral dynamics. Like I said, in this course, we're going to focus more on the longitudinal vehicle dynamics. So I'm going to move fast here. But if you have any questions, I can answer your questions during the discussion session on Tuesday. So please bring questions if you have any. I'm just gonna explain some concepts here regarding lateral dynamics and vertical dynamics. So let's take a quick look at. So when it comes to dynamics, we also have kinematics and kinetics. So here we are talking about kinematics. So when we have vehicle, by the way, this is often called bicycle model, or 2 degrees of freedom bicycle model, because there's velocity, vector, translational motion, and then rotational motion. This is top view, bird's eye view, 2D model. And the vehicle is modeled by a bicycle case model. So if you model your vehicle in this simplified manner, you can get a pretty simplified, manageable model. And this slide shows kinematic relationships of that model, which is like so relating geometry, right? So we have a delta F and alpha F, which is heading angle of the front tire, and flip angle of front tire, which is alpha. And alpha rear is the slip angle of the rear tire. And if we draw a perpendicular line from this is the actual traveling tire traveling vector, right? Speed vector. And if you draw perpendicular lines, and this is this distance is going to be turning radius, so which means your vehicle is turning with respect to this instantaneous point. Okay. And A plus B is this total length, which is wheelbase. You have yaw rate, rotational speed, lateral speed, you have lateral speed, force speed, which is U, then yaw rate. So with those variables, we can write down equations of motions. First, the kinematic relationships, where this is simply writing down the tangent function of delta and f, because we can relate velocity, yaw rate, and speed as a function of delta and alpha. So if you rewrite this, these two equations, one for the front and one for the rear tire, you're going to end up with alpha front, alpha rear, and again by small angle theorem, you are going to end up with these two equations. And if you put those into this kinematic relationship, which is steering angle, front steering angle equals to L over Vx times R minus alpha front plus alpha rear. And then this comes down to these equations. So this is often called Ackermann angle. This is called Ackermann angle. And if you consider slip, then this completes the relationship between front wheel steering angle with slip angles and Ackermann angle. Okay. Again, I'm not going to go through this in detail, but what is important here is that if you write down this equation and put these force values into the equation, the kinematic relationship we derived earlier, then this is what you get, and this term is called understeer gradient. And what this variable is, what this variable represents in real world is, sorry about the font problems, but what this physically means is if k is larger than 0, then it's called understeer. If it's 0, then it's called neutral steer. If it's smaller than 0, then it's oversteer. Why is that? Well, if this value is larger than 0, then front wheel slip is larger than rear. If it's 0, then front wheel slip and rear wheel slip are equal. And if it's lower than 0, then rear wheel slip is larger. And physically, what happens in these two cases is that in the case of understeer, your front wheel slips more than the rear wheel, so it will try to move forward. Okay, and when the vehicle is traveling at high speed and you're trying to turn, and if you have understeer, if you have K larger than 0, then you will have understeer coefficients gradient, and that's the behavior you are going to have. But in the case of K smaller than 0, then you're going to have oversteer behavior. And what that means is rear wheel will slip more than the front wheel. And this is a very dangerous case because your vehicle can spin off. Okay, so usually when you design vehicle, you know, designer always make sure the vehicle has understeer coefficients for this value. But as you go towards sports car or race car, it gets close to neutral steer, and sometimes for race purposes you actually go to oversteer value, and you can actually artificially create that value by pressing on the throttle. Okay. This is vertical dynamics. I think this is very irrelevant to our study, so I'm just gonna skip this part. Okay. So this is it for today. Thank you for your attention, and I'll see you guys on Tuesday. So please bring questions because it's going to be, you know, completely Q&A session. If you don't have any questions, I'm going to try to bring, you know, some questions for you or something to discuss. So hopefully you have better, deeper understanding of something we covered lecture 2 and lecture 3. Okay. All right. Thanks, and have a good weekend, and I'll see you guys on Tuesday. Take care.